In this chapter, we are going to talk about some of my favorite organic reactions, and those are oxidation reduction reactions. And one of the reasons I like those so much is because they're used in industry quite a bit. And so, for example, they are used to turn oils into margarine, right? So from kind of this liquid oil here, this will undergo reduction to form margarine here. And so I really enjoy food science. I think it's a really interesting topic. And so we see that as the application. And so that's one of the reasons these particularly are my favorite chapter. The other reason, so this is an example of hydration and why that's one of my favorite things. But the other reason is that a lot of times oxidation reactions will change color. And I find that to be really fascinating about why things change color in chemistry. Now, before we dive too deep into our reduction reactions, which is really what we're going to cover in this screencast, I want us to go back and review oxidation and reduction of organic molecules. Now, we've talked about this in a previous chapter, so it really should just be a review, but it's always great to dust off those brain cells. So let's review. Oxidation generally results in an increase in the number of carbon, more electronegative atom bonds, right? So an increase in the number of carbon, more electronegative atom bonds. And this is normally carbon oxygen, right? But it could be a lot of things. Or a decrease in the number of carbon hydrogen bonds. Okay. Now, reduction generally is a decrease. It's generally the opposite, right? It's a decrease in the number of carbon, more electronegative atom bonds, right? Or an increase in the number of carbon hydrogen bonds. And we looked at this in a previous chapter where we said, okay, here's the most reduced form of carbon, right? And now we have an oxygen, so we've increased a carbon-oxygen bond between here and here, right? So that is an example of oxidation. So as we go this way, we're oxidizing, and then as we go this way, we are reducing. I want to show you that specifically with your alkenes and alkynes up here. Sometimes two carbons are involved in a single oxidation or reduction reaction, and the net change in the number of carbon hydrogens or carbon more electronegative atom bonds at both atoms need to be looked at. So the conversion of an alkyne to an alkene or an alkene to an alkane are examples of reduction because each process adds two new carbon hydrogen bonds. So just make sure you look for that. And remember, these stick structures are sneaky. They're not going to show you those hydrogens. So it's showing you here, but know that you're not going to see those hydrogens all the time. Now, we're going to talk about three different types of reduction reactions in this screencast. The simplest reduction reaction that we find is using H2, right? Just hydrogen. These are generally carried out with a metal catalyst. The second way you can do this is to use a dissolving metal reduction. Right. In this reduction, right, alkali metals are used as a source of electrons here, and then liquid ammonia is the source of protons. And so this is the second type that we're going to talk about. And then the third type that we're going to talk about use lithium aluminum hydride or sodium borohydride. So H2 is added using a hydride and a proton. So we use lithium aluminum hydride or sodium borohydride. hydride for the reduction. Examples of these are shown here as well. So let's jump in and look at catalytic hydrogenation here. So when we talk about catalytic hydrogenation, the addition of H2 occurs only in the presence of a metal catalyst. And so because we have to use a catalyst, it's called a catalytic hydrogenation. Now, the catalyst here that's a metal, the catalyst here that's a metal is usually palladium, platinum, or nickel, right? And it's absorbed onto a finely divided inert solid such as charcoal. Right? One of the things that we see is that the H2 will add from the same side. So we'll add through a syn addition. So we can see that syn addition here. The different catalysts here generally are chosen because of what's available or what's the cheapest, right? So just kind of be aware of that. Now, so what's the mechanism here? This is the first mechanism where we've really had, say, a catalyst on a solid support. So let's look at that. So in this mechanism, what happens is you have your catalyst solid support here, and the H2 absorbs onto the catalyst just like this. Then you add your double bond, and the double bond complexes with the metal, right? And then the two atoms are transferred to the double bond, and then the double bond leaves the metal catalyst here. So I'm going to tell you right now, it's good to know this. I think it's really interesting, but I am not going to have you draw this mechanism, okay? But it is really neat to see this. And one of the things that's neat for me is when I first learned organic chemistry, we just kind of threw our hands up and said we didn't really know much about the mechanism. And so it's interesting that they've looked at the kind of the migration of the protons and things like that. So maybe the burning question in your heart is, hey, Dr. Pierce, it looks like this is a lot of absorbing and releasing, and I bet there are different rates for different alkenes based on how many R groups they have. And you would be right. So as we're kind of trying to figure out this mechanism, there's a few things that we know. And one of the things that we know is rapid sequential addition of H2 occurs on the side of the alkene that's complex to the metal surface, right? So the metal's on one surface and the alkene comes down on top of it. And then the second thing that we see is that less crowded double bonds, like this one here, will react quicker than more crowded double bonds here due to steric hindrance. And so this also has helped us kind of try to determine that mechanism. Now, maybe the burning question in your heart is, can other double bonds besides alkenes and alkynes be reduced by H2? And the answer is they can. So one of the things that we see is that compounds with carbonyl groups like aldehydes and ketones can also be reduced here. An aldehyde is reduced to a primary alcohol, and a ketone is reduced to a secondary alcohol there. Now, as I mentioned before, hydrogenation is used in industry. When unsaturated vegetable oil, shown here, so we have some double bonds, is treated with hydrogen, some or all of the pi bonds, right, add H2. So when this happens, it increases the melting point of the oil so that now it's a solid at room temperature and it can be spread and therefore can be used as margarine. So margarine is prepared by partially hydrogenating the vegetable oils to give a product that will really closely resemble butter. Now, the steps in hydrogenation of fatty acids are reversible, but what we find is that the hydrogen atoms tend to add sequentially rather than a concerted step, so that we don't just add everything at once. And so what happens then is, even though you have a cis alkene like this, it can isomerize to the more stable trans alkene. And this is a problem because that's how trans fats are formed. And so if you notice, a trans fat here and a saturated fat here have similar shapes. And so the trans fats will stimulate cholesterol synthesis in the liver, and that increases blood cholesterol levels, which can lead to increasing the plaques in the heart, which can lead, of course, to heart attacks. So kind of an interesting health application here when we talk about this. Now, let's talk about the reduction of alkynes. We've spent a lot of time on alkenes. Let's talk about alkynes. We have 3 different ways where H2 can add to the triple bond. It can add twice and form all single bonds. It can add once and have a syn addition where you end up with a cis alkene, or you can have an anti-addition where you end up with a trans alkene. So let's look here at the first one, where we have an alkene that's treated with 2 or more equivalents of hydrogen and palladium. So when this occurs, right, we have 4 new bonds that are formed. We cannot isolate the cis alkene. It just goes straight, boom, to that, right? And remember I said this was kind of tricky because we don't show the protons in, or the hydrogens in these stick structures. So it could just look like this, right? So make sure that you're kind of paying attention because, like I said, it can be really tricky here. Now, to stop the alkene at the to stop this synthesis at the alkene, you need to use a less active catalyst. And the less active catalyst that is typically used is something called the Lindlar catalyst here. So palladium metal is just too reactive to stop at that alkene level. So to stop at the cis alkene, this stops at the cis alkene. Right? You use the Lindlar catalyst. This catalyst is deactivated. So it's a deactivated catalyst, which means sometimes it's also called a poisoned catalyst. You can see it written in a couple different ways. You can see just Lindlar catalyst written under here. You can see palladium on calcium carbonate and quinoline here. So just kind of be aware of that. But most often you're going to see it as just Lindlar catalyst. So with the Lindlar catalyst, just one equivalent adds to the alkyne to form the cis product. And then that cis product is unreactive in further reduction. So we just stop here. Now, maybe the burning question in your heart is, well, what about trans? We know trans adds with an anti-addition. Well, when we do this, we use a dissolving metal reduction. And so the dissolving metal that we use is something like sodium with ammonia, right? And so this ends up with the elements of H2 here being added in an anti-fashion to give the trans alkene. And again, I like to show both of these because, you know, when you show trans without the hydrogens, it's going to look like a Z here. A cis will look like a U shape. Okay, so let's look at this mechanism. When we look at this mechanism, we are going to start out with our friendly alkyne here. And what happens is sodium metal will give up an electron. And that electron will come here and attack one of the carbons on the alkene, and then that electron will go here onto that carbon. Now, this forms a radical anion. Where we have one unpaired electron here. So I want to remind you that that one unpaired electron means that it's a radical. It's carrying a negative charge, and that's what makes it an anion. So then what happens is we have NH3 that comes along, and these electrons steal a proton. And those electrons go on the nitrogen. So now we've added that hydrogen. Right? And we still have that radical. So another molecule of sodium comes along. And the radical adds right here. And so then you end up with a pair of electrons with a negative charge there. So we just end up with a normal carbanion. And so these electrons now will come down and grab that proton, and those electrons go on the nitrogen. And now we've added the hydrogens in a trans fashion. The dissolving metal reduction here is stereoselective because it forms the trans product exclusively. So when we talk about a reaction, I just want to remind you that stereoselective, right, it forms one isomer selectively. So it forms the trans isomer selectively, right? Now, the dissolving metal reduction will always form the more stable trans product. The reason that this is that when you look at the carbanions, so there's a carbanion here that would give us the cis, and then there's a carbanion here that gives us the trans. This intermediate is more stable when the larger R groups are farther apart than when the larger R groups are right here. There's a lot of steric hindrance. And so this is what leads us to have the trans stereoisomer being formed. So this is the more stable intermediate that we see. So let's look at a summary of alkyne reactions. We see alkynes here. We can add H2 and palladium and carbon. We can add H2 with a Lindlar catalyst and get cis. We can add the dissolving metal and get trans. So we can go from an alkene to a cis. We can go from an alkyne to an alkane. We can go from an alkyne to a cis-alkene. And then we can go from an alkyne to a trans-alkene. Now, I mentioned that we'd learn about 3 different ways to do hydrogenation, and so I haven't mentioned lithium aluminum hydride yet. So alkyl halides can be reduced to alkanes with lithium aluminum hydride. And one of the things that we see here, right, is we have an alkyl halide, we add lithium aluminum hydride, and we get an alkane. Okay, and that's kind of where our reactivity stops. Now, epoxide rings can also be opened with lithium aluminum hydride to form alcohols, which is kind of interesting. And so here are 2 kind of examples of mechanisms that we see, right? Where when we look at the lithium aluminum hydride, we see that the hydride is what's reacting here. And so this hydrogen is taking its 2 electrons to form the new bond here. When it attacks the epoxide, it's going to attack at the less substituted carbon, the less sterically hindered carbon, and open up this way. And so we end up with this molecule, and then we add water to protonate the alcohol, so we end up with an uncharged molecule here. Let's look at an example of lithium aluminum hydride reacting with an alkyl halide. And so when we look at that mechanism, we see sort of the same thing here where we have aluminum, right, with its negative charge. And the hydride is what comes in here and reacts with that partial positive carbon, and those electrons go on to the halogen. So this is an SN2 reaction. When this occurs, right, we end up with our alkane. All right, so this is an SN2 reaction. We see that this is a hydride that is being transferred here. So these electrons are the ones that are forming that new bond there. All right, so this ends for us our discussion of reduction reactions. As always, if you have any questions, please feel free to reach out.